Welcome. In this mini lecture, we're going to cover one key idea from sections 11.1 and 11.2, the idea of equivalence relations. So we're going to let A be a set, and we're going to let R be a relation on that set A. So if you recall, we noted that our relation is reflexive if x is related to x for each x. We noted that it was symmetric if x was related to y, then y must also be related to x. And it was transitive if we knew that if x was related to y and y was related to z, then x would be related to z. If our relation is reflexive, symmetric, and transitive, we call this an equivalence relation on A. So now let's look at a couple of relations and see which of these properties hold. For our first relation, we're going to consider the set of pairs xy in z cross z such that x divides y. So let us begin by examining whether or not this would be reflexive. In fact, this will be reflexive because for every element we choose, it will always divide itself. So how do we go about proving this? First, we're going to choose an arbitrary element in our set. So we're going to let x be an element of z. Since we can write x as x times 1, and 1 happens to be an integer, it follows from the definition of divides that x divides x, and that works for every single one. So we know that x is related to x for all of our x's. Now what about symmetric? Is it the case that if x divides y, then y will also divide x? Well, if we think about this, that's not necessarily true. For a counterexample, there are lots of things we could consider, but if we specifically let x equal 2 and y equal 6, we would have that 2 divides 6, but 6 does not divide 2. Hence, in this case, 2 is related to 6, but 6 is not related to 2. So this relation is not symmetric. How about transitive? As it turns out, this is transitive, and we can prove this by supposing that we have three integers, say x, y, and z, such that x divides y and y divides z. In this case, by the definition of divides, we can write y equals xk and z equals ym for some integers k and m. Then we can note that z is equal to ym, but we know that y is equal to xk, which we in turn can write as x km. So this tells us that we must have that x divides z. Hence, we've satisfied the transitive property. That is x related to y and y related to z implies that x is related to z. So this relation, x divides y, is reflexive, it is transitive, but it's not symmetric, so it's not an equivalence relation. Now let's consider R to be the relation on the integers defined by 3x minus 7y is even. So we're going to show that this is in fact an equivalence relation. So we need to show that it's reflexive, symmetric, and transitive. So for our proof, we're going to let x, y, and z be integers. To show that it's reflexive, we will choose x to be an integer, and then we consider 3x minus 7x, which happens to be a negative 4x, which is a 2 times a negative 2x. So here we see that 3x minus 7 is clearly even. And so we know that our relation is reflexive. Now let's consider symmetric. We will start by supposing that x is related to y. So, since x is related to y, we know that 3x minus 7y is even. Thus, by the definition of even, we know that 3x minus 7y will have to equal 2k for some integer k. Then, we want to consider 3y minus 7x. Well, another way we could write that would be to write it as 3x minus 7y minus 10x plus 10y. So, if we note, that's an equivalent form of 3y minus 7x, but what it allows us to do is to adjust our thinking here. Now, what do we have? We've got 3x minus 7y, which we know is even, which we can write as 2k, minus 10x plus 10y. And now we can factor out a 2, which will leave us with 2 times an integer, which we know is even. So thus, we know that 3y minus 7x is even, so we know that, in this case, y is also related to x. So the last thing we need to show is transitive. So we will begin by supposing that x is related to y and y is related to z. So again, the definition of even tells us that 3x minus 7y has to equal 2k, and that 3y minus 7z has to equal 2m for some integers k and m. And so now, if we go ahead and add them up, what do we have? We have 3x minus 7y plus 3y minus 7z. Well, that would have to be 2k plus 2m. And on the left, we get 3x minus 4y minus 7z equals 2k plus 2m, which leaves us with 3x minus 7z is equal to 2k plus 2m plus 4y. This makes us happy because now we can take out a 2 on the right, and so we are guaranteed that 3x minus, we're guaranteed that 3x minus 7z is even, which in turn guarantees us that x is related to z. So, because we've shown that R is reflexive, symmetric, and transitive, R is an equivalence relation. So, anytime we can show that a relation R is reflexive, symmetric, and transitive, we know that it's an equivalence relation. So this is hopefully making you wonder, why would we care about equivalence relations? You'll have to tune in next time to find out. Have a great day. Thanks for listening.